To kick off today's video, I've got a little brain teaser for you all. You'll have 5 seconds to solve the following anagram. Ready? Go! It's pretty tricky, right? Maybe if we plugged this into an anagram solver, it would be able to work it out. But this cryptic message was released in 1655, and nobody was able to decipher its meaning in the 3 years that followed. Back then, astronomers used this technique of alphabetizing the letters in a particular sentence in order to claim a scientific discovery before the full results were ready for publication. This message was published by a scientist named Christian Huygens, and in 1659 he revealed it to mean, well, I'll just let you read it. This Latin sentence roughly translates to, Saturn is surrounded by a thin, flat ring, nowhere touching, inclined to the ecliptic. Huygens had realised that Saturn was surrounded by a ring system. It was Galileo Galilei who first noticed that Saturn was accompanied by some sort of elliptical feature, but it was Huygens, through his homemade telescope, who deduced that this was a ring system independent to the body of Saturn, and in doing so, he opened up a new paradigm in planetary science. The bold, brilliant and bedazzling rings of Saturn have intrigued us ever since, and new technology has led us to discover ring systems all over the solar system and elsewhere in the galaxy. And this incredible, beautiful natural phenomenon is going to be our topic today. A planetary ring system is a flat, disc-shaped collection of billions of particles and chunks, known as moonlets, which are orbiting along the ecliptic plane of a planet. As planets rotate, the force exerted causes them to bulge slightly at their equators. This defines an equatorial plane for the planet, along which satellite material tends to orbit. As such, the moonlets within a ring system experience only very minor vertical motion. Rings can be millions of kilometers in diameter, yet only a few dozen meters thick. The structure of these systems is impressively complex and sculpted by gravity, both from the host planet and from the moons elsewhere in the system. Within the vicinity of a ring system, the tidal stresses from the parent planet are too strong for the moon-forming process of co-accretion to occur, and so rather than collecting to form new moons, the moonlets within a ring system are kept in a fine state. They can be anywhere from molecule-sized to house-sized, but they don't get any larger than that. Each individual moonlet in a ring system can be thought of as its own tiny moon, taking its own path around the planet. Moonlets on the inner part of a ring system complete orbits quicker than those on the outside, which causes the disk to fragment into several narrower, denser, so-called ringlets. And they themselves are made up of dozens of even smaller, ribbon-like lanes of particles. Of course, Saturn's rings are by far the most fantastic, and indeed the most studied in the solar system. But the Voyager spacecraft in the 1980s revealed to us that each of the 4 gas giants houses a ring system, but each varies wildly in its composition, arrangement, and overall substantiality. The rings of Saturn are made up of highly reflective water ice, whereas the rings of Uranus are made from organic material as dark as charcoal. Jupiter's enormous yet faint ring system is composed mostly of ancient dust, and Neptune's rings are a mixture of dust and shredded rocks, floating around in the darkness. We don't fully understand the underlying mechanisms that connect these ring systems, and it's likely that each has a different story to tell. But one thing we do know is that ring systems almost certainly need moons to be both created and sustained. If it were not for the tidal interactions and orbital resonances of the gas giants' moons, much of the material we see in their ring systems would be flung out into space. Therefore, it may be the case that ring systems exist wherever there are moons to be found. not just around gas giants, but around Earth-sized worlds, brown dwarfs, infant stars, dwarf planets, and even moons themselves. Any world can have a ring system if the prerequisites are right. But what are those prerequisites? Well, there are two main hypotheses for how ring systems come to be formed. The first hypothesis states that ring systems can be formed during the birth of the parent planet, from leftover dust and material which is too close to the planet's surface to be able to coalesce into a moon. The second is the breakup hypothesis, which states that rings are the result of shattered moons, which either got too close to their parent planet or were involved in a collision which shredded them down into chunks which dissolved. In both cases, the gravity of the host planet plays a key role. Where two celestial bodies of differing masses exist, for example a large planet and a small moon, there comes a distance between the two objects, known as the Roche limit, where the tidal stresses from the larger body will exceed the smaller body's ability to keep itself held together, causing the smaller body to be pulled apart and dissolved into moonlets. This material then collects along the common plane of the planet into a disk comprised of tiny individual chunks, each with a much lower mass than the moon that came before it. And because they lie within the Roche limit of their host, anytime these moonlets come together to form anything larger than house-sized boulders, tidal forces will break it back down. Co-accretion becomes impossible. Of course, the more massive an object is, the stronger its ability will be to keep itself held together through gravity. And so that's why we see moons orbiting in, around and between ringlets without breaking up. Their gravity is much stronger than that of the moonlet chunks, and so they would need to get a lot closer to the parent planet before they succumbed to tidal forces. Such a fate awaits Neptune's moon of Triton in about 3.5 billion years. Triton's decelerating orbit is bringing it ever closer to Neptune, and it will eventually draw so close that it will be ripped apart by tidal forces, forming bright and brilliant new icy rings around the planet. This is how we think Saturn, Neptune, Uranus, and the dwarf planet Haumea got their rings. As for Jupiter, well, they are more likely to be primordial in origin, and so it would seem that we have evidence of both ring-forming hypotheses playing out right here in our own backyard. But of course, Jupiter's ancient and tenuous ring system is nothing when compared to that of its sibling. In fact, nothing quite compares to the rings of Saturn. They are by far the planet's most distinguished feature, and indeed one of the most breathtaking sights in the solar system, stretching out into space and gleaming under the light of the sun. The rings extend over the 140,000 kilometers, more than twice that of Saturn itself, yet they are only around 20 meters thick on average. The striking, shining protuberances they give Saturn stuck out to early astronomers where other ring systems remained hidden. As we mentioned at the start, it was Galileo who first noticed Saturn's rings, but he was unable to accurately describe them, initially mistaking them for handles or ears of the large planet. It took another 5 decades for us to realise that the rings are not part of the planet itself, and another 200 years to accept that the rings themselves are not a solid structure. Though they appear as one from the point of view of the Earth, the system is separated into several subdivisions labelled A through G, based on the order in which they were identified. The rings D, C, B, A and F lie on the inside, with E and G further out, separated by gaps and trails through which Saturn's moons have passed and cleared out material. These 7 main rings are themselves composed of much smaller ringlets. There may be as many as 500 to 1,000 of them in total. From the very inside, the rings would appear much like floating in a cloud of snowballs and snowflakes, with icy dust and hailstones streaming around in between. While the Cassini spacecraft didn't manage to get this close, it nonetheless revealed activity within the rings on wildly differing timescales, from months and years to just a matter of days. As moonlit chunks come together and interact, reverberations cascade through their surroundings, like gravitational ripples in a lake of ice. Given that the rings are so water ice rich, it's very unlikely that they are primordial in origin. If they had formed from the protoplanetary dust which gave rise to Saturn, then they would not be nearly this reflective. But instead, they shine due to their high water ice content. This suggests that the rings were formed through the breakup of one of Saturn's icy moons, a possibility proposed by none other than the architect of the Roche limit, Edouard Roche, in 1849. It is thought that a moon, perhaps similar to Titan or smaller, may have gotten too close to Saturn. Rather than the whole body dissolving completely, the ill-fated moon would have had its water ice mantle and crust ripped off by tidal stresses, leaving only the dense rocky core intact. The dead core of this moon would have fallen straight into the gas giant, with the residue of its icy exterior collecting into the ring system of particles that we see today, surviving over billions of years as one of the solar system's great wonders. These rings, in particular the E-ring, also receive a little extra assistance in staying so bright, thanks to Saturn's cryovolcanic moon of Enceladus, which erupts plumes of liquid water and water ice into space, feeding the E-ring and providing a fresh source of icy material. While not as bright, striking or complex as those of Saturn, the ring system surrounding Uranus is still both captivating and mysterious. Unlike Saturn, Uranus's rings do not shine. Quite the opposite, in fact. Its moonlets constitute dark and unreflective rocks between 20 centimeters and 20 meters in diameter, suggesting that they are made of organic materials such as hydrocarbons, the likes of which are more prevalent in the outer solar system. In addition, Uranus's 10 closest satellites appear to share compositional characteristics with the ring material, suggesting that this ring system may also have been formed by a shattered moon, but a much smaller moon and not one made of water ice. Uranus's ring system is composed of 11 fine ringlets, much thinner than those of Saturn, making them even trickier to spot. Due to their low reflectivity, we didn't know that these rings existed for the longest time. It was only in 1977, when Uranus passed in front of a star that was under observation, that we noticed the rings trailing the planet. This transit allowed us to count 9 rings back then, and 2 more were discovered in 1986 when we first saw the planet up close through Voyager. The most substantial ringlet is the Epsilon ring, about 100 kilometers wide and no more than 100 meters thick, orbiting at twice the distance of Uranus's outer edge, well within the planet's Roche limit. The Epsilon ring probably contains more than 10 times the material of the other 10 rings put together. Most of the other rings are no more than around 10 kilometers wide, and this rigorously fine structure suggests that something is keeping the ringlets bound tightly, preventing material from spreading out into space. So what might be causing this? Well, as we mentioned earlier, moons play a key role in shaping and maintaining ring systems, and in addition to its rings, Uranus is also home to no less than 27 moons, many of which are small but orbit within the ring system and exert tidal forces. And this is how we think the rings stay so fine. The Epsilon ring is circled by 2 small moons, each around 50 kilometers in diameter, Cordelia and Ophelia. These moons provide like-for-like gravitational kicks as they move round the ringlet, and as moonlets within the Epsilon ring begin to spread out, the 2 moons pass either side, and the balanced gravity of each shepherds the material back into place in the ring. Thus, Cordelia and Ophelia are referred to as shepherd moons, satellites which exert counterbalancing influences on particles within a ring system, neatly preserving the structure in a never-ending game of moonlit volleyball. A similar process plays out within Saturn's rings. Areas in the F ring split and segment into strands which diverge from one another, but are pushed back into place by Saturn's shepherd moons Pandora and Prometheus. Neptune also houses a tenuous, dusty ring system, which is comprised of narrow ringlets similar to Uranus, implying that it may also have shepherd moon satellites which keep its rings bound. Unfortunately though, shepherd moons like Cordelia and Ophelia are incredibly small and difficult to identify within a ring system of moonlets from a passing spacecraft like Voyager. And so it's likely that both ice giants still have undiscovered satellites which shepherd their ring systems and keep them in the state that we see today. Alright, time for the big finish, and I mean really big finish. We know hardly anything about ring systems lying beyond the solar system, but we've managed to identify one simply because of its staggering size. It's likely that ring systems are present in other planetary systems like ours, but the problem is we can't see them by looking through a telescope. In fact, we can't even see extrasolar planets that way. Instead, we detect exoplanets by waiting for them to pass in front of their parent star relative to the Earth and block out some of the light. Then we are able to reverse engineer some of the properties of what's transiting by mapping the light curve of the star. Unfortunately, this transit technology is only just about able to identify planets with accuracy. It simply doesn't have the sensitivity to detect the average ring system from so far away. However, there is one ring system out there that is so large that it was simply unmissable. When an object transits in front of a star and blocks out the light reaching Earth, for planets we can expect a dip in brightness of a few % at most. For larger and more obstructive objects, such as clouds of dust and gas, up to 1/5 of the light can be extinguished. But when we saw a transit which blocked out a whopping 95% of its parent star's light, it left us scratching our heads. First noted in 2007, V1400 Centauri is a young star system around 400 light-years away from the Earth, within the constellation of Centaurus. And while the system was under observation, scientists recorded an eclipse event of the parent star which lasted for some 56 days. Sometimes the star's light was almost entirely extinguished, but other times light was able to penetrate through clear and definite gaps in whatever was transiting. In 2012, a team led by astronomer Eric Mamajek proposed that the transiting object, also known as J1407b, is a large and massive gas giant or brown dwarf surrounded by a ring system of epic proportions. In 2015, new analysis and research allowed astronomers to model the system, revealing over 30 nearly opaque rings, each millions of kilometers wide. The whole system is an incredible 120 million kilometers in diameter, more than 200 times the diameter of Saturn's icy rings. If J1407b were to replace Saturn in the solar system, then its rings would dominate the night and daytime sky like so. At this size, it's very unlikely that the rings were formed by the breakup of a moon. You'd need to grind up all of Jupiter and Saturn's large moons and then some to create this much material. Rather, this ring system has probably formed via the other hypothesis we mentioned. They are primordial in origin. J1407b is a young gas giant in the final stages of planetary formation, and these rings may not actually be traditional rings, but rather a planetary disk from within which the gas giant has formed. The material in these rings consists mostly of protoplanetary dust, and will lay the foundations for co-accretion, the birthing of new natural satellites. Because of the system's enormous scale, The vast majority of this material lies well outside the planet's Roche limit, and so it will be able to accrete into larger bodies, and we believe that this is already happening. Even though J1407b's eclipse event lasted for weeks, astronomers noticed variations in the star's light curve as frequently as on hourly timescales, owing to fine structures which are forming inside. In addition, astronomers have noted a definite gap in the ring system around 0.4 astronomical units away from the planet, where we think that an exomoon has formed and cleared a trail in the dust. And over the next few million years, the majority of this material will condense into large and complex satellites like Europa, Enceladus, Titan and Ganymede. The planet J1407b is known as a super Saturn, being larger and more massive than our familiar gas giant. And it boasts a lot of potential for a rich subsystem of moons on a scale much greater than the ones we see around the gas giants today. But we have caught this system in its fledgling stages. It'll be millions of years before these new moons form, and so we probably won't be around to see it unfold. A reminder of the enormous timescales we're dealing with when waiting for things to happen in space. But hey, at least we've got something pretty spectacular to observe in its place in the meantime. Perhaps when the James Webb Telescope finally launches, its unparalleled sensitivity and detail will help us to peer deeper into this unique system.